and welcome to another Think of a Number. I want to tax your brains now. I'm going to show you a picture, and I want somebody to shout out and tell me exactly what it is. You ready? Go. What is it?
Light bulb.
What kind of light bulb?
10,000 watts.
10,000 watt light bulb. That's brilliant. Just having a light snack. The reason I asked about that light bulb was because that is what this program is all about. It's about something we could not do without. Light. Oh, can we have a ray of light, please? Go over. Oh, thank you. Hip hip, hooray. Now, the light's shining on me, and you can see me now, and you should be able to see our studio audience because they're here somewhere. There you are. It's quite bright, isn't it, that light? Well, they're all there. How many of you got brothers and sisters? Lots of them. Good, all of them, I think. Good heavens, that's incredible. Well, there's nothing on this program to do with brothers and sisters, but we will be talking about relativity later and the speed of light. We'll also be reflecting on how light travels in straight lines, but can be bent into a whole rainbow of colours. We'll be looking at light that you can't see, and we'll be seeing how light could possibly solve the energy crisis. Because if it doesn't, the future could be very, very black. Oh no, the lights have gone out again. Hang on. What's happening? Perhaps Father Christmas is coming now, this very minute. Do you believe in Father Christmas?
No.
Oh! They don't believe in Father Christmas. Surely you believe... I can't believe it. I think the reason people don't believe in Father Christmas is because they can't believe that he could possibly visit every house in the world in one night. Well, I think he can do it. And I think the way he does it is to do with Rudolph's nose. Because Rudolph, as you know, has got a very special nose. He picked it himself. And this is the only nose of its kind. He doesn't want the light to escape. So he chases after it at the same speed, the speed of light, dragging the sleigh and Father Christmas with him. Which would explain how they got round the Earth. Because travelling at the speed of light, they could go round the Earth 7.5 times every single second. So they'd be able to cover all the landmass on Earth in less than 8 hours. And then by staying on the dark side of the Earth, the night would last 24 hours. And they could visit every home. How many homes? There's about 1 billion homes in the world. So they could visit every one if he didn't stay long. And I believe he doesn't stay long. At your house, he probably stays about 86.5 millionths of a second. Which explains why you don't see him. It also explains why he comes down the chimney. He hasn't got time to open the door. Talking about time and opening doors, there's a clock. And here is a watch. Watch? The watch. Very good. Now, this is my digital watch. It's called the digital watch because to move the numbers, I have to push it with my digit. You see? That's all right. It's because once you can understand how Father Christmas gets about by travelling at the speed of light, you may be able to understand the theory of relativity because it's all to do with light. Let me show you. Here's a watch that says 12 o'clock. And there's a clock that says 11:59 or a minute to 12. Why? Well, imagine that that clock is 11 million miles away. Because that's how far light travels in 1 minute. So if that was 11 million miles away, it would take the light a minute to get here, so the clock would seem to be a minute slower. All right? You happy so far? Good, good, good. That says 11:59. Now that clock is going, and so am I. I'm going in this direction at the speed of light. So watch carefully, or you'll miss me. Ready? Go! I've been travelling 1 minute. I've gone 11 million miles. And that clock is changing. Let's see what time it says now. 11:59 and 35 seconds. Now why is that? The reason is, although I've travelled 11 million miles, light coming from that clock has taken a lot longer to come along this line. It's actually taken 1 minute 25 seconds. So if you take 1 minute 25 seconds off that, 11:59 and 35 seconds. I'm going a bit further, in fact twice as far. Here I go. I've been going 2 minutes. And the clock now says 11:59 and 46 seconds. Because it takes 2 minutes and 14 seconds to get here. So that clock is going at a very odd time. Let's go a lot further. 15 minutes I've been going. The clock says 11:59 and 58 seconds. Still 2 seconds to 12 o'clock. If I go twice as far, What did I say now? 11:59 and 59 seconds. It only went a second for all that time. If I go twice as far again, I've been going an hour, but this clock will now only say 11:59 and 59 and a half seconds. And it will never reach 12 o'clock. Why? Well, because that's what happens when you go at the speed of light. Everything seems to change. Time is different according to where you are. The only thing that's constant, catch this. Well done, you've stopped time. But the only thing that's constant is the speed of light. And time always depends on where you are and what you're watching. Well, we're all here in the television studio. You're watching me, and at home, you're watching your television. And the signal is coming from the transmitter to your television set at the speed of light. And the colours and everything to do with television is picked out by light. In fact, you could say that television is a medium totally reliant on light. Do you want to watch television? There you are, several of them. All with pictures, and we've got some more over here. Bring this one on here. This is my special one. And there's another one coming out. Okay. So there you are. You've all got a television to watch. And have you got one to watch at home? Oh, of course. You won't be watching. Yes, right. Some of you, though, may have a black and white television. Well, that's all right. Because we can take the colour out of this set and make it black and white. There we are. You see, a colour television camera is really 3 cameras in one. One for red, one for blue, and one for green. So, I can make that, by switching one of those cameras in, I can make the picture completely red, because I'm blushing. Completely blue, like the inside of a fridge, or completely green, like a cabbage now, or I can mix them all up and have colour. And there they are. Now, just as you can add colours one by one to make a complete colour picture, you can also take colours away. And if you take them away one at a time, you can make certain colours disappear. See what I mean? Have we got the people in T-shirts, please? Yellow and blue T-shirts. Can you come out? Put that there. Got a few things to do. Hang on. Put that there. Put that there. Can you hold that for a second? I'll look at you first. Because you're in a yellow T-shirt, aren't you? So if we take the yellow away from the picture, your shirt will disappear and we'll see what's inside you. And there it's happened, look. That's your inside. Hang on, what have you had for dinner? There's a half-eaten kipper there. You could save that for tea. All right, you come out of it. What that actually is, you see, is this card that's superimposed on the space when we've taken your shirt away. So you come out and you go in there now. That's lovely. What's your name? I'm sorry. Russell. And yours is? Catherine. I forgot to ask her. Okay, Russell. You stand there. Now, you've got a blue shirt and a blue background here. So if we take blue away, the whole lot should disappear, and we should be left with your head. And I'm holding a plate here. And we might just get your head on a plate. And there you are. With your head on the plate. Can you see it? Don't bob about. I'll drop you. Look straight up at my face. Look straight up in the sky. There we are. Oh, Russell! Okay. Fair enough. There you are. Your head on a plate. Right. Thanks very much, Russell. Do you want to take the tray with you? And if you go and sit down, and you come in here... No, hang on. I haven't finished speaking. You stand there. Because you don't have to walk back to your seat. We can actually put you in your seat. I want you to stand here and look at the fellow over there, all right? In that direction there. And we should be able to take away the background and put the audience in its place. And there you are, sitting back in your seat. Isn't that incredible? Right? Okay, thanks. Well, you can walk back to your seat now. Can you give him a round of applause? Because he's done so well. So there you are. Television relies very much on colour. And colour is only part of the spectrum, just a little bit. I've got a map of the spectrum here. It didn't come out very well. We need it tightening up at this end. Oh, that's lovely. Thank you very much. There's a fella behind there. Now, here's the visible spectrum. What we get from the sun is white light, but it really is made up of all the colours of the rainbow. And you can see it being split up when you see a rainbow in the sky. Now, here, there's a form of light that we can't see called ultraviolet light. And this is the kind of light that gives you sunburn, produces vitamin D in the body. In fact, a lot of it that comes from the sun is soaked up by the atmosphere, which is just as well, because it would burn us all up. However, ultraviolet light can be used in other ways. Here's a white card. If I shine ultraviolet light onto it, it illuminates these letters. The letters have been treated with fluorescent paint. And the light is coming from a fluorescent bulb with ultraviolet light. Do you see? I can switch it on and off. So, ultraviolet light can be used in security. You can make a mark with fluorescent paint that can't be seen on something like a banknote. Shine ultraviolet light onto it, and you can see it. Some more light you can't see, it's about here. It's called infrared. And that is the heat source. You heat a red-hot poker, it glows, and that's infrared that's glowing. In fact, when the red is faded, infrared's still coming out of it. Infrared radiation is coming from our bodies. Can I sit here? Are you feeling warm?
Yeah.
I'm roasting, and that's all infrared. Now, we've got an infrared camera over here. That's that one there. Okay. And we've got an infrared lamp up there. Now, it doesn't look as though it's on, because infrared is invisible. But it is on, shining at us. And if you look at the monitors now, you'll see two pictures. The top one is the actual television picture, and the bottom one is an infrared picture. Now, watch what happens when we fade the lights out in the studio. The lights are going, we're all in the dark. And yet, amazingly, you can still see us on the screen. And we're lit by infrared. I've got a candle here. Can you hold that? I just found it. We can only just see it, can't we? We're nearly in the dark. Now watch what happens when I light the candle. See, the match flares up because the camera is sensitive to heat. And you get two great flares. Okay? Now, snuff of that. Oh, lights on. Thanks very much. Have you got my glasses? Yes. So there we are. There's just two kinds of light that we can't see. But there's a whole spectrum of light, all coming from the sun. So let's have a closer look at the sun. The sun is 330,000 times more massive than the Earth. And it's like a gigantic hydrogen bomb continually exploding. All the energy on Earth has come originally from the sun. In a square metre, there's enough energy to boil a kettle every 20 seconds. If only we could harness that energy. So let's see how we're getting on in harnessing the sun. Quite recently, somebody decided to hold a competition to build a car powered by just one single solar cell. That's a solar cell. And the heat from the studio is making the wheels turn around. So can somebody come out and could you come out and help? I want you to let this one go first. Put them over there and then just take the shield off. This one was made by the post office. And here it comes. It might just stick, that's right. And there it goes. Made out of balsa wood, a small electric motor, and one cell. Can you stand the next one down? This was made by Pi. It's a very successful one. Fair whizzes along, doesn't it? But the winner of the competition became the Rolls-Royce of solar-powered cars, was made by Rolls-Royce. And here it comes. And it travelled, I'll send it back. It travelled at about 6 miles an hour. Can you stop it just before it hits the rail? That's it. I'll send the others back as well. Now if you scale that speed up, that's 6 miles an hour, it's equivalent to about 144 miles an hour. But that doesn't mean that they can make a Rolls-Royce car, solar-powered, travel at 144 miles an hour. There are massive problems to overcome. But people all over the world are trying to harness that power from the sun. And there is one machine that has actually functioned and carried a man in flight, a solar-powered plane. Now, this is just a model of it. In fact, it's only 1/10 the size of the actual plane. It's called Solar One, and it's British. Prop at the front, and the wings covered in solar panels. Now, 10 times that big, the actual plane. So if I was standing here, hello, you can sit down now if you like. Thanks a lot. If I was standing here, the wingtip would be the girl on the end in the yellow, could you raise your hand? The wingtip would be about there. And the other wingtip would be the same distance in that direction. Unless, of course, it crashed, in which case the wingtips could be everywhere. But it hadn't crashed, it's actually flown. It's flown to a height of 80 feet. It's flown at about 54 knots. It doesn't take off till it's going about 18 or 20 knots. And it's travelled for 3/4 of a mile, at least. But every sunny day, they're trying to improve this plane. And who knows, in the very near future, we might get it to fly quite a distance. And won't take too long before they'll be attempting to cross the channel. Let's have a puzzle now. Who's got a blindfold? You got a blindfold. Could you blindfold me? Because I'm going to do this trick without the aid of any light whatsoever. Ah, have you done this before? Is he pretty good at it? Oh, that's lovely. Right, I can't see a thing. Now, somebody had a piece of paper. Can you give me the piece of paper? And I want to ask you, I'm going to tear this piece of paper up, and I want to ask the people in the audience, is there anybody who likes sunbathing, who really likes soaking up the sun? Is there anybody? Yes. Oh, good. That's lovely. Right. I want you to give, I'll just tear this paper up, and I want you to give that person a piece of paper. Okay. Give them that piece of paper, and a pencil. Who's got a pencil? Somebody's got pencils. Right? And people who don't like sunbathing, are there many of those? Are there? Yes. I can't see a thing. Right. Some more piece of paper. Give them all a piece of paper and a pencil. And when you've got a piece of paper each and a pencil, I want you to write a 3-figure number. Somebody's dropped all the pencils, I think. A 3-figure number, a number between 100 and 1,000 on the paper. As soon as you've finished, pass them back to my helpers here, and you can put the pieces of paper in my hands. Okay, is that the lot?
Yes.
Oh, it's the lot, right. I'll shove them up, right. Now take this blindfold off. Can't get it off! Oh, it wasn't a bad job. Now, I don't know where these pieces of paper came from, but you can always tell when somebody likes the sun, because they seem to radiate heat. So just by feeling their piece of paper, I should be able to tell which one really liked the sun. And I think it's the person who wrote 106. Is that right? Yeah. That's really amazing, isn't it? Actually, it's not. It's a trick. And if you'd like to know how to do the trick, drop me a line, Johnny Ball, think of a number, and I'll explain, because it's really nothing to do with the sun. But the sun is very important. And somehow we've got to crack our energy crisis. And the aim is to build solar panels in space. Send a rocket up so that we get the radiation from the sun before it hits the atmosphere. These solar panels could be perhaps miles square, always facing the sun, sunbathing, basking in the radiant heat, gathering the energy and beaming it down to Earth. That's the plan. If we do that, we may have at last conquered our energy problems. Because if we can do that, we will never run out of energy. Goodbye. And welcome to another Think of a Number. I want to tax your brains now. I'm going to show you a picture, and I want somebody to shout out and tell me exactly what is it. You ready? Go. What is it?
Light bulb.
What kind of light bulb?
10,000 watts.
10,000 watt light bulb. That's brilliant. Just having a light snack. The reason I asked about that light bulb was because that is what this program is all about. It's about something we could not do without. Light. Oh. Can we have a ray of light, please? Can we have a... Oh, thank you. Hip, hip, hooray. Now, the light's shining on me, and you can see me now, and you should be able to see our studio audience, because they're here somewhere. There you are. It's quite bright, isn't it, that light? Well, they're all there. How many of you got brothers and sisters? Lots of them. Good, all of them, I think. Good heavens, that's incredible. Well, there's nothing on this program to do with brothers and sisters, but we will be talking about relativity later, and the speed of light. We'll also be reflecting on how light travels in straight lines, but can be bent into a whole rainbow of colours. We'll be looking at light that you can't see, and we'll be seeing how light could possibly solve the energy crisis. Because if it doesn't, the future could be very, very black. Oh no, the lights have gone out again. Hang on, what's happening? is coming now, this very minute. Do you believe in Father Christmas? No. Oh! They don't believe in Father Christmas. Surely you believe... I can't believe it. I think the reason people don't believe in Father Christmas is because they can't believe that he could possibly visit every house in the world in one night. Well, I think he can do it. And I think the way he does it is to do with Rudolph's nose. Because Rudolph, as you know, has got a very special nose. He picked it himself. And this is the only nose of its kind. He doesn't want the light to escape. So he chases after it at the same speed, the speed of light, dragging the sleigh and Father Christmas with him. Which would explain how they got round the Earth. Because travelling at the speed of light, they could go round the Earth 7.5 times every single second. So they'd be able to cover all the landmass on Earth in less than 8 hours. And then by staying on the dark side of the Earth, the night would last 24 hours. And they could visit every home. How many homes? There's about 1 billion homes in the world. So they could visit every one if he didn't stay long. And I believe he doesn't stay long. At your house, he probably stays about 86.5 millionths of a second. Which explains why you don't see him. It also explains why he comes down the chimney. He hasn't got time to open the door. Talking about time and opening doors, there's a clock. And here, there's a watch. Watch? The watch. Very good. Now, this is my digital watch. It's called the digital watch because to move the numbers, I have to push it with my digit. You see? That's all right. It's because once you can understand how Father Christmas gets about by travelling at the speed of light, you may be able to understand the theory of relativity because it's all to do with light. Let me show you. Here's a watch that's...